This is Angela Rasmussen from the University of Utah Electrical and Computer Engineering Department, and I'm going to go over an example today of the RLC in a series configuration when the transition is underdamped. So we're going to look at this circuit here, and in this circuit the switch moves from position 1 to position 2 at time equals 0. So here is a summary of steps. First, determine is it series or parallel, then determine alpha and omega naught. From there, compare the two to determine how it's transitioning between initial and final value, whichever direction it's going, and that will be overdamped, underdamped, or critically damped. And then from there, you're going to look at the general form solution and look at the variables that it needs in it. The initial values, final values, if you need the damping frequency, S1, S2 as far as the roots, any other variables you need, you'll need to find for that. And then that will give you the solution for either VC if you're in series, IL if you're in parallel. And then you're going to plug in those values into those VC or IL equations. So first step is series or parallel. So we're going to look at the final circuit to determine whether it's in series or parallel configuration. So here is as it switches, the final position would be in position 2, and we can see that L and C are going to be in series in this connection. So we're going to go with a series connection, and with series we look at the table and we can determine alpha and omega naught, and so alpha in this case is going to be 1 over 2 RC. And this is an interesting case because in the final position is where you're going to look for R, and in this case there is no R. So what do you do in this case is that R is, did I write this? Sorry, I wrote this wrong. I was going to say R is going to be 0. And so R over 2L is the series alpha. And with R at 0, you're going to have alpha is 0. And then omega naught is going to be 1 over square root of LC. And because alpha is 0, it's got to be underdamped because alpha has got to be less than omega naught. So we have an underdamped situation, and so we look again at the table, and we're going to use underdamped here. And so for this equation, we need to know omega d, which is that damping frequency, VC at infinity, and then VC of 0, and IC of 0. So those are going to be, at 0 is the initial values. So I typically find it when it's at the initial values. So we're going to find t equals 0 minus. So the first position, which is at 1, and then you need to determine what is happening with the inductor and capacitor. And so inductor sitting for a long time becomes a wire, and the capacitor sitting for a long time becomes an open. So there is no current, so IL will be 0 here. And then with no current, there's no voltage drop across that resistance of R here, and so VC is going to be V naught. And then at the switch time, 0 plus, that's when you're going to determine the initial value. And so you're going to use that the inductor had a 0 current, and the voltage across this is V naught. And we need to find IC. And the switch is in the second position, and so because there's no current source is 0, IC has got to be 0 also. Then in the final position, you're going to have the second switch and a wire and then an open, and VC is got to be 0 in this case. So the final value will be 0 also. So we have VC at infinity was 0. VC initial was V naught. And IC of 0 was 0. And so now we need to find D1 and D2. So VC of 0 was V naught, and infinity was 0. So D1 is V naught. And then IC of 0 was 0. And VC of 0 was V naught. And VC at infinity was 0, and alpha was 0. So that puts D2 at 0. And so rewriting this, you're going to have VC of t is going to have e raised to the minus 0 for alpha t. Remember, e raised to 0 becomes a 1. And then we have d1, which is v naught cosine omega d t. And d2 is 0. And vc of infinity is 0. So this is an interesting case because what this means is that without any resistance there, ideally, it's going to oscillate between the inductor and the capacitor, meaning the inductor is going to supply the capacitor and then the capacitor is going to alternate it back. And so they're going to be giving back and forth and alternating at that omega d damping frequency. And so it behaves just like an oscillator and it never decays. So that would be my answer. And again, this is t greater than 0. So this would be VC of t is just V naught cosine omega dt. All right, thanks for watching.